Hello everyone, thank you for joining today. My name is Willem and today we're going to look at elastic potential energy. So we have a few learning objectives and that's to define elastic potential energy, be able to understand what effects EPE, elastic potential energy stored, and to recall that energy, elastic potential in joules is equal to a half times the elastic constant, or rather spring constant, in newtons per meters multiplied by extension squared, also in meters. So if you're ready, let's get right into it. Okay, now let's have a look at what elastic potential energy actually is. Well, elastic potential energy is nothing but energy associated with stretched or compressed objects. Now that's a very important point because a lot of people, they think elastic, they think rubber band, I can stretch a rubber band, it's only stretched objects. No, but it's also compressed objects, as you can see in my diagram here. So the static spring here is just the spring in itself, right? In its normal position, no one's touched it. This is its length, okay? So let's call that its length. Now, when I compress this spring, its extension just equals the new length, so L2 minus, the initial length L1 minus the new length L2. So say the static spring is 10 centimeters and the length of my compressed spring is 5 centimeters. That means my extension, even though it's really a compression, is 5 centimeters. Now again, when I have my stretch spring, say the new length of the spring is 15 centimeters. I just do my well, now because this is larger, right, I can do 15 minus 10 and I know the difference is 5 centimeters, and I know that this is a positive change, meaning that it's an extension, and I know that my compression would usually be a negative change, which means a compression. Okay, so sometimes you might see negatives and positives. Those really just tell you which direction the object is being stretched in. Okay, so now you understand that elastic potential energy is nothing but the energy associated with either stretched or compressed objects, usually springs. Now let's have a look at its equation. So we have E, elastic potential energy, is equal to a half, that's an integer, multiplied by K, which is something called the spring constant. So this tells you how stiff the spring is, right? If you have a very thick spring, it's going to have a very high spring constant, which tells you that a huge amount of energy is actually required to, force rather, is required to stretch the spring itself. And then we have E squared, which is our extension squared. Now the squared is important just like in kinetic energy. Have a look at our units. Ng, as always, joules. Half, just an integer, no units. Our spring constant, newtons per meter, telling you how many newtons, how much force it will take to stretch the spring by a meter, or rather for a certain distance. Then we have our E, extension squared, and that's in just plain old meter. Okay, so those are all of our basings right there. Now let's have a look at how elastic potential energy changes with either spring constant or extension. So again, let's do it down here. EP to a half AE squared. Now let's say for a constant spring constant, so say we have two identical springs, elastic potential energy is directly proportional squared. Now again, so say my extension was to double, my elastic potential energy wouldn't just double as well, it would quadruple, just like in kinetic energy, how your energy quadruples rather than doubles with a doubling velocity. So now let's have a look at EPE is equal to half A squared again. Now let's have a look at a constant extension for two different springs with different spring constants. Well, that's just directly proportional relationship. Okay, so if I double my spring constant, I get double the energy out. Now you understand what the definition of elastic potential energy is, what effects elastic potential energy stored, and